All right, in this problem, we're going to see what region is bounded by those two equations. And then we're going to rotate that whole region around the x-axis and find that volume. To graph these two equations, it probably makes the most sense to just solve each one for y. Taking the cube root of both sides, we'll do it in this first equation. And we get y equals x to the 2/3 power. As for this other equation, if we take a square root of both sides, we should get x to the 3/2 power. As far as the sketch goes, x to the 3/2 power has a power that is bigger than 1, so it should curve upward like this. You'll notice that this 2 in the denominator actually is representing a square root. So we're not allowed to plug negative x values into that function. But of course, up here, when taking a square root of both sides of an equation, we forgot to put our plus and minus in. So the second piece of this equation looks something like that. I'm not sure if this is going to come into play or not, but this is what y squared equals x cubed would look like. As far as y equals x to the 2/3 power goes, x has a power that is less than 1, so it should kind of look like a square root function. Of course, in this case, we are allowed to plug negative values of x in here because you can plug a negative value into a cube root, and what would happen is we would get this other piece of this function over here. Okay, so the region in question is this bit right here, and we're going to rotate that about the x-axis, and we're going to use the washer method, meaning we're going to slice this region up like this. We're going to rotate it around the x-axis, and it's going to give us all of these little volume elements that look like washers. It would be helpful if we noticed right away that this point right here on the end of this region is the point 1, 1. You'll notice that the x value 1 and the y value 1 solve both of these equations, so that's going to be your point of intersection. We also have a point of intersection here at 0, 0, and what that helps us with is when we say that we're integrating with respect to x because the width of each one of these washers is dx, we know that x is going to range from 0 to 1. Okay, let's see if we can set up that integral. In the previous video, we reasoned out that this formula right here makes sense for the washer method, where capital R is our outer radius of our washer, and lowercase r is the inner radius of our washer. And since we're integrating with respect to x, both of these functions should be with respect to x. Looking back at our graph, the outer radius of this washer is given by y cubed equals x squared, which of course earlier we solved to get y equals x to the 2/3 power. Therefore, our capital R is going to be x to the 2/3 power. Our inner radius is going to be given by the equation y squared equals x cubed, and we can solve that, of course, to get y equals x to the 3/2 power, and that x to the 3/2 is going to be our little r. And as we said earlier, we're going to integrate from 0 to 1. Now we can do a bit of algebra, we can integrate, we can simplify, and we'll be finished. X to the 2/3 squared is just x to the 4/3 power. We got that by multiplying our exponents. X to the 3/2 power squared, when we multiply the exponents, is just going to give us x cubed. Now when we integrate, we're going to add 1 to the 4/3 power to get x to the 7/3. Divided by 7/3 is the same as multiplying by 3/7. And when we integrate x cubed, we get 1/4 x to the 4th. Plugging in our upper limit and lower limit of integration gives us something that's fairly simple to simplify. 1 to any power is just 1. 0 to any power is just 0. And we can simplify 3/7 minus 1/4 by hand. I'm getting a final answer of 5/28 pi. And that was a pretty good one. I like that problem. I'll zoom out on it for you so you can see the setup again. And we're finished. I hope you liked it.